Okay, guys, it's time to talk about energy, friction, and efficiency, and how it relates to mechanical systems and simple machines and all this wonderful stuff that we have been talking about. We're going to talk about a little bit about work and energy and how, with energy, we can't really make it, we can't really destroy it and get rid of it, but it can transfer from one form to another. This might happen when you flick the switch on your for the lights in your home, and we get a change from electrical energy into light energy. It could be something like this when you throw a baseball, and that baseball goes from you ate some food, you got that chemical potential energy, and that changed into the energy of motion, kinetic energy. You can drop something. So right now, everything that is under the force of gravity, it has gravitational potential energy, and we can change this into kinetic energy by dropping something as well. So we can't create it, we can't destroy it, but it can change forms. That's what we mean by transfer. The energy is moving from one form to another. Energy is the ability to do work, so yeah, we need it. That's why we are eating some food and every day. And we think about it, light is a form of energy. It gets captured by the leaves of plants and by photosynthesis. Plants make their own food, and sometimes we eat plants or eat things that eat plants. So we gain that chemical potential energy from food, and we can do work. We can move things around. Work being force times distance. So and so if we gain that energy, we also gain that ability to do work as well. Okay, so our work is not always as efficient as we would like to be due to something called friction. So when we have moving parts and things moving against each other, friction opposes the direction in which we want our work to go. Basically, it resists our motion, and and unfortunately it makes things harder. It's kind of like our family's been doing a lot of biking, and sometimes when I go from biking on concrete to biking on grass, it's a little bit harder, and that's because when I bike on grass, there's more friction going on there, and it's harder. I gotta pedal harder to bike on grass. It just happens that way. So in an ideal world, all of the effort and all the energy we're putting into doing a job would go to that specific job that we're doing, but that's not the case. We lose some of our energy due to friction and other forms of energy. Friction creates heat, and so we're always losing a little bit. And so if you think of if you're going somewhere, you hop in the van or hop in the car with mom and dad, and the engine turns on, and it would be great if all of that gas that is being burned to move a car, it would be amazing if all of that gas was being used to get you from point A to point B. But it's not. A lot of it, as soon as you turn the key, you can hear the engine. So energy is being lost as sound energy. If you could flip the hood after you arrived at your destination, you would not want to put your hand on the engine because it's super hot. It would burn you. And so we can say that a lot of energy is also being lost to heat here. So car engines, they're only about, I want to say 40% efficient. So when you travel from one spot to the next, 40% of the gas that you used was used to get you from one spot to another. The remaining 60%, we're losing is heat, sound, maybe there's other things, electricity, maybe there's other things going on in your vehicle as well. Maybe you're listening to the radio, but only 40% is actually being used to move us from here to there. And so, yeah, machines are not 100% efficient, but we can calculate how efficient they are by using this formula. The work done on the load, or the work that's actually being done to do that job, divided by how much work we're putting in by our effort. And so this is the long way of writing it out. When you guys get your problems, I would not write out all those words. You can just use this formula down here to make your lives a little bit easier so you don't have to write as much. Also, if you get into some efficiency calculations and they're out of 3 marks, I want you to show a formula and a substitution and an answer every single time. Efficiency doesn't really have any units except for a percent sign. So I shouldn't see any joules or ohms or newtons or anything like that at the end in your answer for efficiency. I should just see a percentage sign, and that is good enough. If you get an efficiency number that's bigger than 100, 2 things might have happened. 1, you probably got it wrong, and these numbers are backwards, and so you'll have to flip them, because no machine can be more than 100% efficient unless the second option, you discovered some magical new device in which this can happen, in which you will probably win a Nobel Science Award. Good job. But for, I would say, the majority of cases, you probably just got to flip those. If you get an efficiency over 100, there should be alarm bells going off in your brain if that happens. Let's do one example. So we have the work done on a pulley is 7,230 joules. The work done by the effort force is 11,000. What's the efficiency of this simple machine? So I'm going to start with my formula. That's going to be my first mark. Kind of just like when you get your mark test back and you calculate the percentage. Just the total amount is your bottom, which is kind of like this number, and your small number, or hopefully big number on the test, in terms of how much you got right or how much is actually being used to do the job, is that. And then just divide the 2, multiply by 100. Very, very similar. So I'm going to put my 7,230 joules up here, my 11,000 down here, whoops, times 100. Pick up this guy, and it's time to punch in these numbers. 7230 divide sign 11000 equals 65 decimal. So I got, and then times 100, I got 65.72 repeating. 65.72727272727272727272727272 forever and ever. Amen. But I don't want to, percent sign. So the question might tell you how many decimal spots to round to, or round to the nearest whole. If not, I think 1 decimal is fine in this case, so that's what I'm going to do. And I'm just going to call this a 65.7%. This pulley is 65.7% efficient, and I'm going to leave it like that. Next up, there are some ways that we can reduce friction as well. And Because if it's less efficient due to friction and we're just wasting that energy as heat, there are some ways that we can make things a little better. One is by oiling or greasing or lubricating moving parts. That's going to make them slide past each other easier, and we won't, and that will lessen the force of friction. Less heat will be created. So lubricating things is a great idea. Friction always isn't bad though. In some cases, it's very useful. Like, for example, if I'm driving a car and I'm turning, or if I'm on a bike and I'm turning, or even just going straight. If there was no friction, we would not be able to move. But yeah, because there's a little bit of friction between tires and the ground, it allows us to move. And also, if we turned on a bike or car, if there was no friction, we would just fly off into the ditch. We would just keep going straight. But because there's that opposing force, it allows us to make a turn. Also, another example is maybe like at the Amazon warehouse. So some of these conveyor belts that travel upwards. Some are going to go down and some are going to go up. But if you put a box on a conveyor belt and it needs to go up, if there was no friction, the box would just slide down every time. But because there's that opposing force, even under the force of gravity, the box can move up on a conveyor belt, and that is helpful. Friction being used in a useful way. That's it. Take care.